We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, artificial grass. What is the connection between space and this sporty synthetic surface? Electromagnets. The science behind the simple device that controls our everyday gadgets. Medals. The complex manufacturing process behind these badges of honour. We reveal the surprising science and amazing manufacture behind these wicked inventions. Grass is everywhere. Whether it be in our gardens or in the famous sports arenas of the world, this simple plant is a huge part of our daily lives. But what if there's not enough rain to keep the grass green? Or perhaps too many football boots are making it difficult to maintain? Enter artificial grass. Houston, Texas, a place recognized for its links with countless missions to the stars and the base of NASA. It's no surprise that the city's sports stadium and the world's first domed arena was named the Astrodome. Because of the dome, the grass of the playing field soon deteriorated due to a lack of sunlight. An alternative had to be found. The stadium owners decided to replace the grass with the world's first ever artificial playing surface, a green carpet made of nylon fibers. This surface was used for the baseball season of 1966, and a new era in sports was born. It is because of this first use in Houston that artificial grass is often called AstroTurf. In the late 1970s, once artificial grass had been introduced globally, nylon was replaced with a softer, more realistic polypropylene. This reduced risk of player injury. This second generation of turf featured longer tufts, spaced more widely apart, making the grass resemble the real thing even more.
I play football all the time, so artificial turf is like my second home. I've seen it develop a lot over the years. Initially, it was a kind of shorter, kind of artificial surface that used sand, and now, instead of sand, you have these rubber pellets, which is a lot better, kind of, it absorbs a lot more of the shock, and it's being used at training facilities by some of the top clubs in the world. Real Madrid have it at their training complex. I mean, if it's good enough for Real Madrid, it's good enough for me.
The most common material now used is polyethylene, which is even softer and much less harsh on the skin. In sports, rubber granules and sand is added to the surface to ensure that the pitch has the same qualities that real turf has. It's estimated that a modern artificial turf pitch will have 800 million blades of grass. This ever-evolving turf has meant that even the driest of continents can now enjoy sports played on the grass. And as an added bonus, gardeners and groundsmen will never have to worry about mowing the lawn ever again. Artificial Grass Limited and SIS pitches are based on the beautiful western coast of England in Cumbria. They produce top-quality artificial grass that is in use worldwide.
SIS Pitches factory here in Maryport has been here since the end of 2005. It now produces in excess of 530,000 square metres a year, making it the second largest artificial grass tufter in the UK.
The production process begins with tufting machines. These tufting machines are loaded with bobbins of polyethylene and polypropylene yarn, according to the type of order to be fulfilled. The bobbins contain the artificial grass that has been tightly spun to create a green thread. The grass is created by melting down green-coloured plastic pellets that are then formed into plastic blades that match the thickness of grass. Once these blades are produced, they are spilled onto the bobbins, ready to be loaded onto the tufting machine. There are many different combinations of artificial grass that can be produced for varying uses, from football and hockey pitches to grass for the home garden. These yarns can include different shades of green, as well as browner colours to even better mimic real grass. The bobbins are seated in a rack where the yarn unspools and is fed through clear plastic tubing to rollers, which even out the tension. Rows of inline needles arranged horizontally pick up the yarn and stitch it directly into a woven polypropylene backing sheet, being fed through rollers at a precise speed. Underneath the tufting machine is where the real magic happens. Small razors cut the newly threaded yarn, releasing the green blades and allowing it to take the all-important shape and texture of real grass. This whole process happens very fast, with hundreds of rows of stitches being stitched and then cut every minute. Tufters skillfully monitor the process, picking up errors, monitoring for breaks, snags, missed stitches and empty bobbins. The stitched carpet is made into rolls and then transferred to the backing plant. At the backing plant, the stitched carpet rolls are fed onto rollers, which pass through a machine which applies a precise layer of molten latex, which, when cooled and hardened, provides an anchor for the stitching. Exactly the right amount of molten latex is spread onto the roll using a blade. Applying latex means that the yarns are unable to become dislodged when used on the final playing surface or garden.
The latex, when it's going through the ovens, gets up to around about 140 degrees to actually seal it in place. The yarns will stand a temperature of about 70 degrees before they begin to melt. So it's very much a question of balancing temperatures and not overheating the product.
Hot needles then pierce the finished carpet at varying intervals to allow drainage for rainfall or watering when installed.
We perforate the carpets by using specially adapted soldering irons, which will punch 4mm holes into the carpet every 4 inches by 2 inches.
The entire process is closely monitored, as the thickness and consistency of the latex backing is critical to providing a strong, reliable final product. The resulting rolls of finished grass are then ready to be delivered to the gardens and pitches of homes and stadiums worldwide, and await HGV delivery to the client.
Over the years, artificial grass has changed. Many years ago, it would be made from polypropylene, which would have been very abrasive on the skin. Fibres now have been developed so they're extremely soft, but at the same time extremely resilient.
So we've seen the grass being made, and now for the installation. The carpet of artificial grass, which comes in 2-metre or 4-metre wide rolls, is unrolled over the prepared surface and glued into place. Once the grass has been laid, the production process is complete and the surface is ready to be enjoyed by sportsmen and homeowners for years, with no worries about the weeding and grass cutting. Now that is truly a wicked invention. They power a multitude of devices, from the humble electric doorbell to state-of-the-art MRI scanners. They are electromagnets, and we are going to find out how they can allow you to move with ease, comfort and speed, and answer that everyday enigma. Why are magnets horseshoe-shaped? It all started in 1820, when a Danish scientist noticed something strange.
Hans Christian Ørsted took a battery and turned it on and off. He noticed that his compass that was nearby would twitch, and he realised that it was only when it was turning on and then when it was turning off that there was such a twitch. Now, he knows a compass responds to a magnetic field, but didn't understand quite why anything was going on, other than the change in current from the battery turning on and off and powering something must change a magnetic field under which the compass is responding to. That didn't lead to the electromagnet as we know it, but that was the first step.
As we all know, a permanent magnet has 2 poles, a north and a south, and attracts ferrous metals like steel and iron. If you have 2 bar magnets with their ends marked north and south, the north end of one magnet will attract the south end of the other. On the other hand, the north end of one magnet will repel the north end of the other, and both south poles will also repel. What Ørsted had discovered was the ability to switch this magnetism on and off by using electricity. In 1824, British scientist William Sturgeon took Ørsted's discovery and created the world's first electromagnet, which could lift objects roughly 20 times its own weight through the power of magnetism. While electromagnets may have evolved since Sturgeon's original was made, their basic design has remained the same. Mechanically, an electromagnet is pretty simple. It consists of a length of conductive wire, usually copper, wrapped around a piece of metal. The metal needs to be ferrous, which means it needs to contain iron, as this possesses magnetic properties. A current is introduced and flows through the wire. This creates a magnetic field around the coiled wire, magnetizing the metal as if it were a permanent magnet. What makes electromagnets so useful is the ability to turn the magnet on and off, or even reversing the poles with a flick of a switch. With the principle and working models of electromagnets established, the scientists and inventors of the mid-1800s implemented two new innovations that would dramatically improve the electromagnet's performance.
If you take the iron part and bend it into a horseshoe shape, you then have the north and south poles are closer together. They're dipoles, they're opposites, but because they're close together, the magnetic field between them is much, much stronger because the poles are closer together. And take the coil of wire, insulate the coil of wire with plastic, which doesn't affect the magnetic field, which means you can then put lots and lots of turnings, and so you can put a lot of coils of wire around the iron core in a very short space of time and also distance. With this, you can then lift much heavier items, you can generate much better magnetic fields. In the 1800s, they had electromagnets that could lift 3,600 pounds. That's over a ton worth of material back in the 1800s. That's quite an impressive achievement for an electromagnet even today.
So, simply put, the more coils your electromagnet has, and the greater the electricity used, creates the most electromagnetic power. But how do we use these magnetized wonders? The electromagnet's most obvious use is in recycling metal. As a magnet will attract iron-based metals like steel and not other more expensive metals like aluminium, an electromagnet can be used to sort through vast piles of scrap metal. This ability might not sound that amazing, but when you consider total steel production in 2008 reached 1.3 billion tonnes, of which over 500 million tonnes was made from scrap metal, then you can get an idea of an electromagnet's recycling worth. You also come into contact with electromagnets in your everyday life. For example, the hard drive on your computer is arguably an electromagnet, as tiny pieces of metal magnetized by the electricity running through the computer's circuits are embedded onto the disk in patterns representing the saved information. This is why it is not a great idea to put powerful magnets anywhere near your hard drive. MRI scanners, power tools, loudspeakers, toasters, the list is endless and includes that little device you push when you visit your friend's home, the electric doorbell.
Your doorbell works on the principle of an electromagnet. You push the button, it sends a current, then the electromagnet pulls the hammer and hits the bell. And then that breaks the current, which allows the hammer to strike back. And because you're still pushing, then as soon as the circuit is completed, when the bell hits back, it pulls away, comes back, and keeps going back and forth until you have something that hits back and forth and produces a bell, and it's very simple.
One of the most impressive uses of electromagnetism must be the Maglev train. Maglev is short for magnetic levitation, which means that these trains float between 1 and 10 centimeters over a guideway, using the basic principles of magnets rather than the rails and steel wheels of traditional track trains. These trains can reach incredible speeds of up to 310 miles per hour, which would mean you could travel from Paris to Rome in around 2 hours. But how do they work?
What you have is a series of magnets that are tilted in different directions, and they can be turned on and off very quickly. So, the ones that are in front of the train and pointing towards the front of the train will be pulling the train along. The ones behind push and levitate the train, which allows the train to move forward and backwards because they're at alternate angles. What that means is that the train never has any friction with the rails, and means it can actually run faster, smoother, and once the train is moving in a magnetic field, it's actually very hard to derail. So it's actually quite a safe system to be in.
It may be a simple device that we don't really notice, but from doorbells to hyperspeed travel, the electromagnet is truly a wicked invention. Can we make an electromagnet with just a few household items? We're going to need a screw or nail, a paper clip, electrical tape, a coffee cup, 2 drawing pins, copper wire, a battery, and some small pieces of metal like pins and more paper clips. Take the copper wires and wrap them tightly around the nail. The greater the amount of coils, the stronger the magnet. Connect one end of the copper wire to the battery and fix in place with electrical tape. We create a switch using the drawing pins, coffee cup and a paperclip, and connect our DIY electromagnet to the battery. We turn on our amazing electromagnet by swiveling the paperclip so it touches the other drawing pin. This completes a circuit and allows the electricity to flow through the copper wire and makes the whole device magnetic, allowing us to pick up a paperclip or two. We switch our electromagnet off and the paperclips drop. It seems our electromagnet is working. Like an industrial electromagnet, the current flowing through the coil from the battery creates a magnetic field around the coiled wire, which magnetizes the screw as if it was a permanent magnet. Can we make an electromagnet with a few household items? Yes, we can. Wicked challenge smashed. What better way to recognise success than with a shiny medal of commemoration that will stand the test of time? Medals have been awarded for centuries, but do you know just how far back their history goes? Roman emperors would award military medals as well as giving medallions as political gifts that were made much in the same way as coins, which of course the Romans were famous for making. As well as this, the Roman Republic adopted medals as military awards. Different medals would represent different achievements. Modern armies still use medals or military decorations as a way of honouring brave soldiers that have fought in battle. One of the most famous of these is still used today. It is the Victoria Cross. The Victoria Cross was, as the name suggests, first awarded by Queen Victoria in 1856 to honour acts of valour in the Crimean War. Since the Second World War, only 15 Victoria Cross medals have been awarded, making this the highest badge of honour for any soldier serving in the British Army.
So during the Second World War, there were medals awarded for those who served in actual combat, but increasingly you get medals awarded to those who served in a civilian capacity and those who served in different areas which perhaps have been forgotten. And so now it's well noted that people receive medals for all service.
Aside from battle, medals have become synonymous with sporting events. As Olympians compete across the globe, they dream of that gold medal that will commemorate all of their hard work. These medals, symbols of achievement and respect, will continue to grace the chests of soldiers and sportsmen, making medals a truly wicked invention. We've seen how winning a medal is all about keeping cool under pressure. And now we're going to see how extreme pressure produces a medal.
The thing that people don't realise about making a medal is how long that it takes from starting out with a design or a design concept to actually having your gleaming new medals. You should allow something like 10 weeks. It's a 10-week process generally.
The first step in the production of a medal is design. Today, this is achieved digitally on computer software. A 2D design is made of the medal before this is translated to a 3D digital model. Once the model has been made, this is then turned into a mould. For medals with high relief, which basically means a high depth in the design of the metal, a large-scale version of the design is created. This can be produced in one of two ways. The traditional method, which is still used today, is to sculpt onto clay by hand, using fine cutting and grating tools.
For me, I love the carving process because it's something that I lose myself in. I get completely in the zone and I just love doing it. And if I probably had my choice, that's what I'd be doing all the time.
The modern method is to use an engraving machine. This requires a CAD or computer-aided design model to be made digitally. The advantages of the model method is that the design can be repeated infinite times with complete consistency. Once this large-scale model has been made, it is then used to create a steel die. The steel die will later go on to be used to press the metal of the medal. Firstly, the large carved model is placed in a reducing machine. The machine then traces and copies the design from the model that has been carved. The machine then cleverly reduces the diameter of the trace pattern and uses this to cut the design onto a piece of steel. This becomes the steel die. The newly cut steel die is then put onto a lathe, where the die is turned in order to make it exactly the correct diameter. This will later go on to be the diameter of the medal. Once we have the die with the pattern cut and sized exactly right, it must be heat treated. The die is heated to a temperature of exactly 790 degrees in order for the metal to achieve the optimum hardness that will ensure the die will not crack under the extreme pressures of the minting stage. The red hot die is quenched in oil and then tempered back to the correct hardness. Now that we have our finished die, the medal is ready to be minted. To start the minting process, strips of metal are prepared from metal sheets. The sheets are cut to the appropriate size for the completed medal. These blanks are then placed into a hydraulic press that has been fitted with the die. The metal blanks are then stamped at extreme pressures of up to 500 tons. That's the weight of 2 passenger jets or 2.5 Statue of Liberties being pressed down onto the metal. The stamped metal is then heat treated in a process called annealing. It goes through a furnace on a conveyor belt. Annealing basically means softening the metal by heating it. Once it has been annealed, it is then restruck in the press. This is repeated until all the detail from the steel die has been pressed into the metal. Our medal is now taking shape. It is cut to size using a variety of tools, such as lathes, handsaws and sanders. Now the medal can be finished in a series of polishing processes, such as bead blasting, where tiny beads are fired under high pressure at the medal. As well as this, the medal is placed in a machine full of small steel balls and some polishing solution. As the machine vibrates, the medal moves around the bowl and gets gently burnished to make it shiny. The clasp for the medal is also tumbled in a similar way to polish it before being fitted to the medal. At this point, the medal is pretty much complete. From here it can be engraved on the reverse in an engraving machine, as well as having a ribbon fitted to it. With the shiny new medal complete, it's ready to be gifted to the lucky recipient.
The challenge for us really is to make something really beautiful, really attractive design with a nice crisp image, so that, you know, for thousands and thousands of years people will be looking at it and it'll be a credit to the recipient of the medal and also to us, the makers.
Medals, a rewardingly wicked invention. So, there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Artificial grass, electromagnets and medals, all wicked inventions.